We followed the discoveries that revealed invisible monsters lurking at the centers of galaxies. We saw how supermassive black holes grew to billions of times the mass of our sun and shaped the evolution of the universe itself. But all of those discoveries have only shown us what happens outside a black hole. The greatest mystery still remains hidden, beyond the event horizon, beyond the point of no return, a place where every known law of physics is pushed to its absolute limit. For decades, scientists have struggled to answer a question that may be one of the most important in all of science. What truly lies inside a black hole? Does space continue to exist there? Does time survive the journey? Or does reality itself begin to unravel? In this chapter, we will travel beyond the visible universe and venture into one of the most extreme environments ever imagined. We will explore how black holes distort time, how they challenge our understanding of space, whether they could act as gateways through the cosmos, and why they may ultimately hold the key to understanding the deepest secrets of existence itself. Prepare to cross the event horizon. Prepare to leave behind everything familiar, because the journey is about to take us into the heart of the greatest mystery in the universe. This is part 2, Beyond the Event Horizon. Have you ever wondered what truly exists inside a black hole? Not outside it, where modern telescopes can observe glowing disks of matter and enormous jets of plasma, but deep within it, beyond the event horizon, a region of space so mysterious that the familiar laws of physics appear to break down completely. For decades, black holes have been regarded as some of the strangest objects ever created by nature. They emit no light, reflect no light, and are almost impossible to observe directly. Yet these invisible cosmic giants may hold the deepest secrets about the nature of space, time, and perhaps even the origin of the universe itself. One of the most fascinating properties of a black hole is its ability to distort time. According to Albert Einstein's theory of general relativity, gravity is not simply a force pulling objects together. Instead, massive objects warp the fabric of space and time around them. The stronger the gravity, the more severe the distortion becomes. And when space is distorted, time changes as well. This effect is not just a theory. It has been confirmed countless times through modern experiments. The GPS satellites orbiting Earth must constantly adjust their atomic clocks to compensate for differences in the flow of time. Without these corrections, navigation systems around the world would quickly become inaccurate. But near a black hole, the effect becomes far more extreme. Imagine an astronaut slowly approaching the event horizon of a supermassive black hole. To observers on Earth, the astronaut's clock would appear to tick more and more slowly. Every second experienced by the astronaut would seem longer from the perspective of someone far away. As the astronaut gets closer to the event horizon, time appears to slow almost to a standstill. The light signals coming from the spacecraft become increasingly red and faint. Eventually, the astronaut appears frozen forever at the edge of the black hole. Yet, from the astronaut's own perspective, nothing unusual happens. Time continues to flow normally. The spacecraft continues its journey forward. Deeper into the darkness, closer to the greatest mystery hidden within the black hole. And eventually, it approaches what physicists call the singularity. The singularity is the theoretical center of a black hole. It is a place where all the mass of the object is compressed into an unimaginably small region of space. Density becomes infinite. The curvature of space-time becomes infinite as well. At that point, the equations that describe our universe cease to provide meaningful answers. This represents one of the greatest challenges in modern physics. Today, our understanding of reality is built upon two extraordinarily successful theories. General relativity describes gravity and the large-scale structure of the cosmos. Quantum mechanics describes the microscopic world of particles and energy. Both theories are remarkably accurate, yet inside a black hole, they appear to contradict each other. This suggests that our understanding of the universe remains incomplete. Somewhere beyond our current knowledge, there may exist a deeper theory capable of unifying gravity and quantum physics into a single framework. That is why many scientists view black holes as the ultimate natural laboratories.
they offer a unique opportunity to explore the most fundamental laws of reality itself. But the mysteries of black holes do not end there. Some physicists have proposed a far more radical possibility. What if black holes are not the end of a journey? What if they are gateways? Within the mathematical solutions of Einstein's equations lies a hypothetical structure known as a wormhole. Imagine folding a sheet of paper so that two distant points touch each other. A tunnel through the paper could connect those points directly. A wormhole would work in a similar way. If such structures exist, they could create shortcuts across enormous distances in space. Some theories even suggest that wormholes might connect different regions of the universe, different moments in time, or perhaps entirely different universes altogether. It is a breathtaking possibility. However, no observational evidence has ever confirmed the existence of a wormhole. For now, they remain suspended between scientific theory and imagination. Meanwhile, another profound question continues to puzzle physicists. Do black holes live forever? For many years, scientists believed they did. Then, in the 1970s, physicist Stephen Hawking made a revolutionary discovery. According to quantum mechanics, empty space is not truly empty. Throughout the vacuum of space, pairs of particles and antiparticles constantly appear and disappear. Near the event horizon of a black hole, one of these particles may fall inward while the other escapes into space. To a distant observer, the black hole appears to be emitting energy. This phenomenon became known as Hawking radiation. Over unimaginably long periods of time, Hawking radiation causes a black hole to lose mass. It slowly shrinks. It becomes smaller and smaller, and eventually it evaporates completely. For a black hole with the mass of our Sun, this process would take vastly longer than the current age of the universe. For the supermassive black holes found at the centers of galaxies, the timescales become almost impossible to comprehend. Yet even these cosmic giants cannot escape the passage of time forever. If we look trillions upon trillions of years into the future, we may witness a very different universe. Stars will exhaust their fuel, galaxies will stop producing new generations of suns, light will become increasingly rare. The universe will grow colder, darker, and quieter. In that distant era, black holes may become the last dominant objects in existence. They will continue merging with one another, forming even larger structures. But eventually, they too will begin to disappear. One by one, black holes will evaporate through Hawking radiation, until the final black hole vanishes. What remains may be a universe filled only with faint particles drifting through an immense and frozen darkness. Perhaps that is the ultimate fate of everything. Or perhaps it is merely the beginning of a new chapter that we are not yet capable of understanding. And this is why black holes are more than astronomical objects. They are gateways to humanity's greatest questions. What is space? What is time? Does time have a beginning?